Hey all, welcome back. We are continuing our studies about support vector machines. Just a reminder of the concepts. We're looking at the maximal margin classifier, support vector classifier, support vector machines, and how that comes about. Last week, we looked at the concepts, as you can see in the table of contents on the right. And today we will look at the textbook exercises for this chapter. So for the first few, as we were talking about just a couple minutes ago, it's one of those situations where it feels easier to do the homework by hand, by pencil and paper. I did a kind of a brute force approach where I have a bunch of dots around the XY axis and then literally colored them based on the classification later. And before I forget, I also wrote a quick function to compute the accuracy of a confusion matrix. All right, problem number one asked us to graph these two functions here in terms of x1 and x2. That's the equation of a line and an inequality in each instance. And that's what we get here in this picture. For my approach in the data frame, I literally have a column that says if the y value is bigger, color blue, otherwise color red. In part B, pretty similar. We have this inequality pair, and that's the picture that we get. Recall that the concept is that we have what we're calling a separating hyperplane that splits the space into two different regions. In problem number two, we look at a non-linear boundary. The equation that we get is the equation of a circle. So what we have here is the blue region is the area beyond the circle, beyond a radius of 2. And the red region is the circle within a radius of 2. The textbook then asked for these 4 locations, would it be classified as blue or red? And what I did was took the Euclidean distance, the Pythagorean theorem, put that into an if-else statement, which would immediately spit out the answers red or blue. Part D was a bit more conceptual. It says, while this graph is not linear in terms of x1, x2, show that it's linear when you include the quadratic terms. What that means for our purposes is that in addition to the usual beta, not beta 1, x1, beta 2, x2, we can have these additional terms, beta 3, x1 squared, beta 4, x2 squared. And the reason why this counts as linear for our purposes is that if we take the equation at the top here, expand the algebra, we can actually figure out the numbers that go into coefficient spots that makes this work. That is, in particular, there's one copy of x1 squared, so beta 3 is 1, and there's one copy of x2 squared, so beta 4 is 1. In problem number 3, we are given this table of values, and we are asked to graph it and then try to figure out where our separating hyperpoint is. So we could plainly see that we have some red dots and we have some blue dots. Remember, when creating the optimal separating hyperplane, you don't necessarily need all the data. You focus on the places where the dots of opposite colors or opposite classifications are closest. So let's see, is there an annotate button here? So we're looking at these 4 dots because they are closest, or on the right here, we have a red-blue pair that are really close to each other. And on the bottom left here, we have a red-blue pair that are close to each other. So it turns out we could draw the separating hyperplane that separates those pairs, and we don't actually need to worry about the other 3 data points yet. So when we draw the separating hyperplane here in the solid line, that's the location. And then we call the margin goes perpendicularly away from the separating hyperplane out to where we see the data, the closest data points. So the margin would be here, literally the closest distance to the dots. Part C asked us to figure out what the equation was. So that's the equation of the solid black line. In this example, I'm classifying the blue region where we're below the line and the red region where we're above the line. By a little bit of geometry, we could figure out the numerical distance of the margin. So we get about 0.35 here. And as I said above, the margin is defined as the closest dots to the separating hyperplane once we have that in place. So in another point of view, these 4 data points were the support vectors. They're the ones that matter when creating the hyperplane, whereas the 3 dots in gray do not come into the calculation. And thus in part F, let's see, let me double check something real quick. In part F, we're looking at this location here at the coordinates 4, 1. So we're looking at this data point. And if it moves slightly, if we had it over here or maybe over here, the calculations that we discussed last week would say that the separating hyperplane would still be in the same location. because this data point would not be a support vector. Part G is kind of a math teacher question. Sketch a hyperplane that is not optimal. So this time around in the solid black line, I drew a hyperplane that gets kind of maybe too close to the dots. And that has a slightly different equation there in the subtitle. And then part H, another conceptual question. Try to draw an additional observation so that the two classes are no longer separable by a hyperplane. So here I put in this new blue dot way far in the top left. But then the idea is I cannot draw a way that would separate the blue and red dots completely. So then we move on to the applied exercises. As in previous weeks, let me give credit where credit's due. This person, their GitHub repo on me had a lot of good resources here. So for the most part, I'm reading those off to you. In problem number 4, we're working with 100 observations, a simulation, but where there's a non-linear separation. Then the problem will ask us to practice with a polynomial kernel or a radial kernel, and then we need to go back and have a sense of which one did a better job. So they, on me, had this simulation for creating a data frame. Put about 70% in the data in a training set, the remaining 30% in a test set. And that's what we're working with here. We could quickly observe that the separating hyperplane, the linear decision boundary would not completely classify the data here. Hence, we have a non-linear situation. So for a linear kernel, literally putting the word linear in the code, since we will later worry about the bias variance trade-off, we could perform some cross-validation by suggesting various levels for cost. Remember that, as we discussed last week, long story short, cost allows for a little bit of misclassification, some of the data being, say, in different colored dots, for example, in a way that makes it actually easier for the classification or the separation of the data to occur. The higher the cost, the more misclassification that can happen. And the higher the cost, the more flexible your model is, especially with the training data, and less susceptible to overfitting with the test data. However, the higher the cost, the more misclassifications you're going to get, maybe in the first place. So we have a tune function, which I think came from this package here, the E1071. And for the folks in the audience today, it was actually this function here that would not run when I tried to build the book and upload our code, which bothered me a bit because this bit of code here is directly from the textbook. So whenever I ran this code in that particular setting for building the book, I got an error that said these were unused arguments. But on the other hand, you could plainly see I could knit the document elsewhere. Anyways, with these 1, 2, 3, 4, 5, 6, 7 suggestions for cost, what Toon will do is actually build a support vector machine with this kernel on the training set, and building those 7 support vector machines with these various levels of cost, you could literally extract the one that does the best job in terms of probably accuracy. And then here we have a picture of that support vector machine in action. That is, here's our original setting with the green and black dots. And one of the reasons why support vector machines are popular is because nowadays it's relatively small amount of code, and we could classify the information. On my computer, this chunk of code would take slightly long, but still only about 1 or 2 whole seconds. Throughout the exercises that are coming up, we're going to judge whether or not the classification did well with a confusion matrix. The predicted labels on the left, the true labels on the top. Recall that we want to see the biggest numbers on the main diagonal where the predictions match the truth. Otherwise, the numbers on the off diagonal would be the number of misclassifications, the mistakes. It finally occurred to me to write a function to calculate the accuracy rather than having to hand code that. And in this first example on the training set, we're getting an accuracy of about 71%. And it probably comes as no surprise once we move on to the test set that the accuracy might be lower. Accuracy here about 67%. So instead of assuming a linear separation, we could use a radial kernel, literally changing the word here to radial. By the internal mathematics, in addition to recommending some various levels for cost, you have these various levels for gamma, which was kind of the radius of the circles that we're working with. Since now your grid search of the parameters are these costs times these gamma values, this code could run or take longer to run. Just something to be aware of. Nevertheless, the code will once again produce a best model, and that's the picture that we get here. The code is implying that everything in the reddish region should be classified as +1 label. Everything in the yellow region should be classified as a -1 label. But seeing where the X's and and O's are. We get a sense of might be still some misclassifications here. But whoops, I spoke too soon. This time around, with the radial kernels, we do see that everything was classified correctly in the training set and also classified correctly in the testing set. Okay, so now in problem number 5, we're going to work with support vector machines with a nonlinear kernel, but also compare that with logistic regression as far as classification is concerned. Part A asks us to do a simulation or generate synthetic data in 2 variables with about 500 data points with a quadratic decision boundary. The textbook also gives us this code to do so. So we have that quadratic decision boundary there. And when you plot everything, oh, this is the situation that we're dealing with. And you may recall from a math class that the boundary is the equation of a hyperbola. The red and black dots in some regions are really close together. And remember that our support vector machine does allow for some misclassifications. And that's intentional. In part C, we could bring up code from our previous chapter, fit logistic regression. So we're building a generalized linear model, but because of the binomial response, we're careful with the code to put those ideas in so that we are performing logistic regression. At first, at least when I ran the code, we have a lot of misclassifications. So the logistic regression got about 53% accuracy. Of course, anything close to 50% is bad because you might as well just flip a coin or seek out randomness at that point. Because what happened was that the logistic regression, compared to the original picture, the logistic regression made this prediction. Here in part E, we're going to perform logistic regression again, but also include some quadratic terms. A couple warnings appeared, but this time around, the logistic regression got 100% accuracy.
Sorry, what was the I function that you use in that line? I of x1 x squared.
When you build a model in R, when you do y tilde and then followed up by the predictive variables, R doesn't understand at first when you want something to be non-linear, such as x1 squared. So the I function, I forget what it stands for, but it tells R to treat this as a mathematical variable rather than like a data frame variable. And you need that in place when you're talking about polynomials in R.
Okay, so
So with the quadratic terms, with the logistic regression, this time around, it's reproducing the original picture and their classifications. Now that we see that logistic regression works, we're going to try out a support vector classifier. Just for the sake of trying out different models, we're going to start off with a linear model, several different values of cost so that we can perform a little bit of cross-validation. We see many misclassifications, and the accuracy is down to 52.4%, because compared to the original picture, at first the support vector machine actually, as sometimes AI does, just says, why don't we just label everything the same? We see that here, the support vector machine actually predicted everything with this label and just skipped the other label entirely. So thus, we, the analyst, have to guide the program a little bit more this time around with a non-linear kernel or for the support vector machine, switching this out to radial, for example. Remember, with the radial kernel, you have to suggest several values of the cost and for the gamma coefficient. This code takes a little longer to run, but this time around we have much fewer misclassifications. And we're getting an accuracy of about 99%. I think there were 8 problems in total. For problem number 6, we're looking at situations with a small value of cost versus a huge value of cost. Synthetic data in 2 dimensions. And what that person on me did was create this separable set of synthetic data where we do have an obvious margin between them. I think the idea for some of the next few parts is, what if we added some noise to this? So some of the black dots might move, some of the green dots might move, but we're still using the red line as our separating hyperplane. So with some added noise, if we have some black dots and green dots in different locations, the suggestion for the hyperplane is now the blue line, whereas the red line was the original. But the goal of this particular exercise is to look at the range of cost values. So in that situation, we're trying out different levels of cost. when you actually run the tune program, if you look at the output, you get something that looks like this here. So we're performing tenfold cross-validation. With these values of cost. Thus, on one hand, you want to, of course, get the lowest misclassification error, but to avoid overfitting, to avoid variance later, we have this secondary column called dispersion, and you're hoping for the lowest here. Now, getting errors of 0 is probably something faulty with this, maybe my setup or the code. And nevertheless, the idea is to minimize this second column. So the best cost is not, it shouldn't be this 100, but whatever the fourth entry was in the suggested or the manually inputted values, and that we got a cost of 1. So now in part C, we have a test set, but trying out the similar separating hyperplanes from before. We see that with a cost of 0.1, we get an accuracy of about 98.6%. And with a cost of 10, we get an accuracy that's lower. So that is to say, remember that while we could increase cost to help out with flexibility, remember that the accuracy might decrease. Let me say that again. See if I could zoom out. In the top example, we have a cost of 0.1. In the bottom example, we have a cost of 10. And those are the accuracy results. As with the other chapters, the textbook author then recommends that we practice some of these skills on some of the data sets that they have. We're going to look at the auto data set and classify the efficiency of the car, miles per gallon, into high or low gas situations. Remember, we're doing classification problems today, so we need a categorical variable for the response. And that's what this is doing here. Part B, make a support vector classifier, some cross-validation. So once again, while the errors decrease generally when we're increasing the cost, we also are worried about the overfitting. So we look for the situation somewhere where the errors are low and the dispersions are low as well. This time around, out of the suggested cost values, the tuning does extract the best cost, I think, property. And it'll save those values, the best parameter and the best performance as attributes. That is, when you use the tune function, you could go back and extract the best parameter and the best performance value. In part B, we had used a linear or polynomial kernel. So in part C, like in other places, we'll try out a radial kernel, different values of cost, different values of gamma. Skipping the output a bit, we could go and extract the best parameters, like so. I slightly misspoke a minute ago. We could also ask for a polynomial kernel. And when you do that, in addition to the cost value, you ask for degree 1, degree 2, and maybe up to degree 5 as another parameter. Skipping the output, we could once again extract the best parameters. It turns out in the data set about cars and talking about fuel efficiency, the linear polynomial, namely a straight line, was the best situation that it found in this particular grid search. You could also compare these best performance values. And it turned out that for this particular problem, the simplest version of the support vector machine arguably got the best performance. Which goes to show you that in machine learning, sometimes the more complicated models are not the answer. All right, folks, one more problem here. We're looking at the orange juice data set provided by the authors of the ISLR textbook. We have a sample of 800 observations, putting some of those in the training set, some of those in the test set. The model is going to be the purchase variable explained by all the other variables. If we try out this recommended cost value here in part B, when you do the support vector machine calculation, you could run the summary command on that model to see information such as the number of support vectors. Remember that the original data had 800 data points. So if we have 438 support vectors, that means we're using more than half of them, half of the data as support vectors. Which may be good and may be bad. It's situationally dependent. At the moment, for the linear kernel, we have an error rate of 16%, where the error rate is the complement of the accuracy. An error rate of 16% on the training set. And on the testing set, an error rate of about 19%. Thus, if you have your code set up, you realize that you want to not only use one value of cost, you want to try out several different values for the sake of cross-validation. You run this through the tune command. And now looking at the best model, on the training set, the error is slightly decreased down to 16%. On the testing set, slightly decreased down to 18%. And so far in part E, that was on a linear kernel. So then you, the machine learning analyst, would then try this out on a radial kernel. Nice thing is at this point, you just copy paste the code. You only need to change out the kernel. On the training set, the error rate is about 15%. But the error rate is higher on the testing set. So at first, what happened was on the training set, the radial kernel seemed to do pretty well. But then on the testing set, the radial kernel actually did worse than the previous attempts. So then finally, part G asks us to practice with a polynomial kernel. Try out a second degree polynomial at first. The error rate goes down to about 13.62%, but on the training set, but then the error rate is higher on the testing set. All these numbers for the error rates are relatively close together. It's just something to keep in mind on. And the textbook authors probably wanted us to focus more on practicing our skills rather than getting excellent results. All right, folks, so that actually brings us to the end of the exercises. Was there anything you want to go back and check out?
Was good.
Yeah, same for me. It was interesting the part where you mentioned that the simpler model, you're only using a linear decision boundary turned out best. I think in the previous exercise.
Yep, that was this one here.
Okay. So if there is nothing more to add, we really have a presenter for the